So thank you for joining. I'm Nurit Dor, working at Certora for more than 4 years, almost from the very start. I'm a VP product, and I'm happy to go over with you on something that I've learned over the few past years on how do we check specification, and how do we what can we say about the quality of properties that have been written and checked, and many of what we're going to see is based on real problems that we have encountered during the years we are working, and we have built many solutions and methodologies for how to check the spec. So please stop me if you have questions. You can either post them in the chat and we will read them off. I'll be happy to take questions while we are going over.
To a quick question, Reed, people can follow your code is available. People can follow your presentation.
Yeah, so I shared the slides already in the chat. Anyone can open it, and we can follow the links together, so we can look at different ones together, and I can take questions on each one, and we can. So because when looking at counterexample, it really helps to have access. I'm also assuming some familiarity with the Certora Prover and CVL, but I'll do it slowly. And if there are questions, please also stop me and I'll answer. Okay, so let's first of all break two myths. So if my rules are verified, that implies that I'm done. So no, definitely no, big no. It means that we need to start checking, okay? Because rules have bugs and we need to check the rules. Rules are just like writing in any other programs, okay? So you won't write your program and say, okay, I'm done. You will start testing and doing a lot of testing. We know that studies have shown that the amount of effort in testing is even more than development. So even here, testing the rules should be considered a big task, very time-consuming. Writing the rules is also time-consuming, so it has to be taken into account. The other thing, so if I have a rule for each function, does that mean that I have 100% coverage? Now, what is exactly coverage? We know from testing that there are different measurements for coverage. There is line coverage, there is branch coverage. In formal verification, what is even coverage mean? But definitely no. What we know for sure is that the formal verification is only as good as the specification. Okay, so if someone says, I have formally verified this and that protocol, the question is, what is the specification? Which properties have been proven? Okay. Now, the common problems we see in spec, and this is, again, all based on real problems that we have seen, cases that were even caused to miss bugs. So it's very important to know them. There is vacuity, tautology. There is what we call limited scope. This is a little bit not well defined, but vacuity and tautologies are terminologies that you can just look them up. And there is the biggest problem, the missing property. So let's first of all understand a little bit the different. So vacuity. So a rule is violated when there is a state that reaches the assert and the assert does not hold. Now, this implies that if there is no state, there can never be a violation. Okay, and let's take a look at this very, very simple rule. Let's say I have X and Y, and I require that X is greater than Y, but also that Y is greater than X. there is no possible values for X and Y that can obey this requirement. Nothing in the world can hold on this require. It's the equivalent of require false. That means that whatever I will write in this assert, it is verified. So I can write X equal 5, it will be verified. I will write X not equal 5, it will also be verified. And this is one of the main problems, but this actually we have a very, very good solution. We check, first of all, that the assert is reachable, that there is at least one state that can reach this assert. So that's our vacuity check. We will see it. Let's go over tautology. Tautology is an expression that is always true regardless of the code, okay? It's like saying 1 is equal 1, X equals X. This is based on a real example that we have actually seen and reviewed. There is some getter, X is assigned some getter. There is another variable Y that is assumed to be different than X. Then I hope everyone is familiar with this syntax. This is a parametric rule, meaning that we check now each and every function in the contract. And then we want to assert that the sum getter is not X or sum getter is not Y. Okay, so for this to be violated, both expressions have to be false. And that means that sum getter equals X and sum getter equals Y. But we said that X doesn't equal Y. So it will always be true. Just based on this require and this assert statement, it doesn't matter what. We can change the functions. We can change everything. There is nothing that can violate this. Now, the assert is reachable. It's just always true. It's the equivalent of assert true. Okay, the next problem, this is harder. We call this a limited scope. Limited scope means that your rule is not a vacuous. Your rule is not a tautology, but it is checking something very, very small. It can be either that it is checking a very specific path. It can be that it's checking very specific values. It can be that a combination of requires or something like that causes the rule to be checked on a very small set of the cases that can actually occur. These ones are actually harder to find, but we will see additional technology that we have that can make you think again, okay, and reason again what is the scope. So let's look at this rule. X equals 0 implies that some computation is also 0. So it is only checking the case that X is 0. It is not checking if compute X equals 0. Does that mean that X can only be 0, right? It's only the direction that if X equals 0, then compute X equals 0. I'm missing here an assert, but this is the basic idea is that it's checking very, very small. Now, the missing property, that's probably the hardest. Again, we'll see technology that can make you think what are the properties that are missing, but we cannot say this exact property is missing. And those are the things that we didn't think about when we designed the spec, or we did think about, but we didn't get to write them, to work on them due to some kind of time limit. And it is important to know this, okay? Because that means that there might be a hidden bug still there, and it's important either to fill in this property or really do an extra audit or something like that, or use other technology in order to get into some confidence. Okay, so if no questions, then are there any questions? So let's go into a few of the techniques to check specification, and we'll just practice it over the Raft code that was unfortunately lately hacked. So the first thing is code review. Just like we do code review for code, but there are different things that we should look at. We have the sanity check, that's a tool. Mutation testing is another tool that we have developed and is very useful in understanding the coverage. And we even have something that is called coverage. It's a new feature that we have, and I'll discuss it just a little bit. Okay, so when we do code review, we look at a few things. Okay, we need to understand, of course, the system. It's very hard to do code review of a specification without, first of all, understanding the system. And then we need to look at the rules, and we need to understand, are there any unsafe assumptions? Those are assumptions that either due to some kind even of setup, the taste is the way that we invoke the prover, and it can also be on a rule-to-rule basis. Those would be like requires that you might say, wait, this require can be, there are cases where this require will not hold. And then I'm looking for each rule, I'm asking myself, can I make it stronger? Can I make it check something else? Or can I have it check on more cases? For example, it's checking only one function. Can I have it check additional functions? And then I'm thinking about what properties can be added. And the last thing, this is also related to that limited, I'm going to ask myself which scenarios are covered. And here I'm going to use a lot the satisfy command that we have. So I want to change my rule a little bit to make sure the cases that are covered. Okay, so let's go into the code. I'm going to go over Raft code, and we have a set of specification files, and we'll focus now on one file that is called the ERC20 indexable. This is an ERC20 that is the liquidity token, and it is for representing that collateral has been given, and you know, the way we think about LP tokens. Okay, so let's review the rules together, and I'll be happy if you can share here ideas. The first rule is that check functions that can change a balance. Okay, what we see here is that basically the assert saying that the balance of a message sender has to be what it was before. And the way this rule is written is by filtering out all the function that can change the balance of. So all the other functions should just leave it as it is. So this is a nice rule. It checks that there is no side effect to the balance besides this three function. But it doesn't check anything about this three function and how do they change the balance of, right? So definitely, right, we can have a rule or even add to this rule, right, that if it is mint, then we expect the user balance to be increased, maybe stay the same, but definitely probably not be less than. Same for a burn, it should be reduced, and many more cases. Additional rule, check current index cannot be 0. Okay, this is an interesting one. There are two requires here. There is one require backing amount that the rule starts with assuming that it is not 0. And there is some explanation here that this has been checked and this is a safe assumption. But what about starting with the current index not equal 0? So what happens if it is 0? The rule doesn't check, right? Maybe if it is 0, it has to stay 0, right? Maybe it should never be 0, and then we actually need to check this okay? That it can actually never even start at 0, because here it's basically saying if it wasn't 0 in the beginning and backing them out is not 0, and we call set index, it cannot get into 0. Maybe there's another function that can make the current index be 0. So this is, looking at this without too much understanding of the code makes me wonder if this can be stronger, okay? First of all, check more functions. Check also the case that it can never be 0 after the constructor. So I might even have this as an invariant, what we call, and then we check that it's never 0 in the beginning and it's never, can never be 0. Okay. And this is the last rule that Raft have wrote for this file. Check total supply must be greater or equal than the sum of the user balance. So there's an assumption of 2 users, and there is this require that the balance of the 2 users equal total supply. This, as we can assume, is definitely not a safe assumption, right? There can be 3 users, there can be just 1 user, and what if there is a bug in the code and the balance of a user can be greater than the total supply? Then we are not checking that, right? We are checking that if we are started in this state, then the balance of the 2 users is less than, this is also the less I would doubt it, and I will try to make it stronger by making the assert equal here. But I guess, right, there can be actually adding here another user. I will take all of that into account. Now, that's it. Now, thinking about more properties is rather easy in this case, because I do feel that the coverage is very low. And, you know, there is hardly any, the main function here are actually the mint and the burn. And there is not that many functions that are checking this, right? Mint and burn are filtered out here. And here there is a call to mint and burn, but it's only checking that the sum of the balances is less than the total supply. So let's add another rule. And the type of rules that I really like to add for things like mint, burn, and almost any operation that a user can do is a rule that compares 2 scenarios. The scenarios I want to compare is if I mint to some address X and I do another operation and I mint Y, how is this compared to minting in one step X plus Y? Okay, we would expect that doing 2 operations, a user cannot benefit from this, okay? So it's very easy to write this type of rules in Certora. I'll just give the general idea, and then we can take a rule that I prepared already. So we have what we call a storage variable. And the storage variable represents all the state of all the contracts. And now I can do this operation, mint X and then mint Y. And now I can check the balance of 2 before. Notice that I don't need, so this will be after 2 steps, balance of 2. And now I want to run mint on the sum X plus Y in one step at the state that I had before. So it's like rolling back to that state and doing a different operation. And now I can check what is the balance of 2 after one step. And now I want to assert. So my assert will be that after 2-step should never be beneficial to a user, right? It should be always, he should get either less or equal is, I guess, okay. So this is the general idea of the rule. I'm missing here a little bit part. I need to define variables, and we also have the end. So I've written this. So I wrote it for mint, and immediately copy paste. I wrote it also for burn.
Maybe, Nurit, if I can interrupt for a little bit for people who are not familiar with CVL. These are basically comparing programs. It's like, we call it sometimes relational properties. You are asking the prover to compare between two programs. And it's essentially, we are checking a monotonicity. Basically, every DeFi protocol has to have it. In some sense, these are properties too good to start with, because you don't need to understand a lot about your protocol to write these kind of rules. Of course, sometimes you want to prove correctness, you need to prove more interesting rules. But the interesting thing about these rules that Nurit and Shoam wrote, they are something that you can start with writing these rules. You can actually start with these kind of rules, right, Nurit?
Yes, exactly. Okay, so we are comparing two cases here. And this is a very strong way to check a lot of the properties that are very, very important. And it's very easy to write it because you have this storage, so it's very easy to reason about one case and then immediately compare it to another case. Maybe I should also add that you don't need to initialize anything here, right? It doesn't mean that I'm starting with balance of 2, 0 at the beginning. I'm starting with any possible. I'm starting with the case that it's 0. I'm starting with the case that it's almost max unit. So we are reasoning about all the different cases. We are reasoning about 2 is the message sender. So here is a full one. We have this end variable that represents the environment, the message sender, the block timestamp. So we are reasoning about the case that the 2 is both the message sender, but a different user. We are taking account here many, many cases, right? Notice that basically we don't have here any assumptions in this rule. There is no require beside assuming that this doesn't overflow. It will give us very good coverage. And if we will go and see a result of a run of this, I need my, am I sharing my,
Yes,
yes. Yeah, okay. And here, let me paste this so we can also all look at this result. Okay, so yeah, whoever wants to open, and let's look at that additivity mint that is violated in this case. I don't know if you're not familiar, let me a little bit explain. So this means that there is a violation. We provide here a set of the values, a concrete counter example, and we have here the call trace. So what we see here, we have after 2 steps. Oh, this one is a huge difference. Everyone is a little bit different in the asserter approver. So after 1 step and after, no, this, wait, I think I might have been running this. Let me check a different, this will be a bit, so sometimes, let's take this one, sorry. I'll edit Okay. This is the additivity only for the mint case. And here the numbers will be nicer. So after 2 steps, it is 15, and after 1 step is 14. So now we can start looking what actually happened here. And we can see that mint of 1 returned 4, okay? And again, mint of 1 returned additional 4, but mint of 2 was just 7, okay? Now, this is not a good behavior, right? We don't want it to be that by splitting my operation to 2 steps, to 2 transactions, I can actually gain for that. It means that it's on behalf of someone else. It means that usually there is some kind of a bad behavior that right, rounding error or something like that is not in favor of the system. It's in favor of the specific operation. And we can go back to the code and now look a little bit, right? We already see here the div up, and we can look again to the code. And we see here indeed that the mint computes the amount, but it divides up according to the stored index. And we can look at the div up function. And it's basically adding +1 to the division. So, right, whenever we do an operation, we will get 1. And this is exactly the case that we see in the counter example. And this is the root cause of the hack that Raft had. And what the hacker did is that by splitting an operation to 50 steps, he got more and more liquidity tokens. He also had to a little bit manipulate the stored index with a flash loan, but that if this wouldn't have been in favor of the user, he wouldn't have gotten that much right tokens. So that's the basic idea of the bug. The last thing I wanted to share about code review is really understand the scenarios that are covered. And here we have a new command. It's rather new, called satisfy. And the idea is that when a rule is satisfied, where it is verified, I can ask the prover, give me a witness, okay? So the idea is that I will go to my code and I will change this idea to satisfy. And now the prover will give me a witness, a good example. And I might see that it's satisfied and I might not be happy with the case. I will see that, wait, it's satisfied only on X0, Y0. That's not good enough for me. So I will make it give me a better case, satisfy X greater than 0 and Y greater than 0, okay? I might want to see a case that it's equal, okay? Because I say less than equal, then I might ask the prover, is there a case that it can actually be equality, or is it always that a user loses by doing 2 steps? So I can play a little bit with the code, and then that can also give me some confidence. Let me show you how the report looks like for a case with satisfy. Here, satisfy. No, okay, yeah. So it's not satisfied. It's a parametric rule, but it's not satisfied on all the codes. So this is not too much interesting, but here we have call to the mint, and we ask to satisfy the case here is that the total supply stays less than the, right? Less than the total supply is greater than the balance of the two users. And here is a case where it's really a very limited case. So I might go back and ask the prover, give me something more interesting. Wait, so this is true. This is the mint, and it's a mint of amount 0. So I might go back now to my rule, and I want to see a witness. We call this witnesses. I want to see a witness that it's not 0. Just to make sure that for some reason, the only case that we cover here is that amount is 0. Okay, it might be a bug in the code even, that there is some problem, and any value that is greater than 0 is actually reverting. Okay, so it can really help also check the code and check the spec. Okay, any questions on satisfy and code review, spec manual review, like we do code review? Okay, so let's go into some of the technologies that we have. Am I sharing? Yeah.
Actually, no, I do have a question. Do you have examples where we have satisfy in a customer's CI? So not using satisfy for debugging.
Yes, yes. So satisfy is a rule. For example, where you want to say that a good scenario can happen, use the satisfy. For example, you want to say that this function should not always revert, use a satisfy. Or you want to say it is possible for me to deposit and then withdraw all the amount I deposited. That would be a rule for a satisfy. If you try it with assert, you might get a violation due to rounding, but you might want to prove that if you give a very beneficial amount, right, something that you computed that you don't lose, then you might get everything back. Yeah, thank you. Good question. Okay, so now let's look a little bit on the technology that we have. So the first thing that we have, and we have this for a long time, and almost all of our users use this constantly. We recommend actually running this all the time. This is a flag that is called rule sanity. It has two modes. It has the basic mode that actually has no false positive. Whenever there is some sanity problem on the basic, it means that it's a real problem. And the things that we are checking here is the vacuity and the tautology of invariants. We can see here an example. So we have this vacuity mistake. This is basically the example that we have seen before. No, it's a little bit different. This is a case. There is it's a management system. It's based on a real example that we have seen, that there is a pending manager that can claim the management, but it has to be the message sender. So if we'll go to the code, I hope you all know you can see the code also from Certo Approver, which is very, so claim management can only be activated by the current pending manager. And here accidentally someone had that the message sender is not the pending, and then this assert is actually not reachable because we have this require and the require inside the claim management contradicting, right? So there might have been a hidden bug here that instead of setting the current manager to be message sender, it would have been address 0, something like that, something very critical. This rule would have missed that bug, okay? But the sanity help us make sure that it's not vacuous. So that is vacuous. Tautology invariant. Again, this is the case where we can check an invariant regardless of the code. So here, for example, it's basically saying, right, not some Boolean implies that the Boolean is false, so it's definitely equivalent. Nothing in the code can break this invariant. The way we check it is that we check if this invariant hold on all possible states, all possible permutations, right? We don't even start, not only on the constructor, we just start with an arbitrary state. If this invariant hold, it means that that's a tautology. There is not even a single state where it can be violated, okay? Okay, so this is the vacuity. The advanced checks a little bit more, and it can be also very interesting. It can help you notice things. Let's look at mistake. So mistake is also a case about the claim management, basically the same idea. And here probably what the user wanted to write is that if the pending manager was pending before the call to claim, then now the current manager is the pending. And what we see here is that this is always false. So it doesn't even matter what you write in this side. Okay, we are not even checking it. This rule is basically verified just because the left-hand side part is always false. Okay, and that means that either you wrote this rule wrong and you wanted to prove that this is false, but usually it means that you're not checking exactly what you wanted. Okay, we have here the ones for Raft. So here there are sanity issues, basically because this code always revert. Okay, so if we go back, we can see here the code. A lot of functions are not supported. Okay. Now, I would have written this differently. I don't like this way it's written. I would have written that there is a set of functions that need always to revert. That's very easy to write with the asserter approver. And then I will filter them from any other rule. That means that I'm checking if someone accidentally changes this, thinks that he needs transfer or something like that, then the spec will break. Okay, so it is safer if you assume that a function always revert, just have a rule on that, and then your sanity will be passing. And on the advanced, we can also see some nice things here. We basically see that I think here on this one, the 0, yeah. We actually see that there is a require that is redundant. So we can prove this rule. Remember this rule with the current index? We can actually prove that this rule also holds when this require that it does not exist, meaning that even if we started with 0, the current index is not 0 after set index, okay? Maybe if it's without set index, maybe there is another thing, but this rule actually doesn't need this require. This means that you can prove something stronger, but it might also mean that maybe you are missing something, right? Because if you think you do need this require, then maybe the code is actually implying that, or maybe there is some other problem in the rule that actually implies this require. So it also can help you think, is this really, really redundant? Does it make sense? Okay. And okay, so we saw one case with the rule structure. Okay. Any questions on wool sanity? Okay, very, very recommending. Basically run it all the time. The basic one, run all the time. The advanced is a bit more time consuming, but it is worth to run it. And I notice sometimes there's a lot of false positives. We will work on improving also this feature, but definitely can highlight problems. Okay, mutation testing. So mutation testing is not something we invented. It is a well-known technique for understanding the quality of testing. The basic idea is that if you change the code under test, and no test fails, that means that you're not covering this line, okay? Or maybe you're not covering this part of the line or something like that. It highlights the quality of testing. So the same idea we are following here. We have Gambit, which is basically just the mutation generator, and we are using it to generate solidity mutation. You can use this also for other testing techniques, but we have it built in for Certora. So we mutate the code and then we check the spec, but we also highly recommend to do manual mutations. The quality of manual testings is very, very important. So even what we suggest is have something from like a red team. And the idea is that not the same person should think about the bug injections as the person that wrote the properties. Because when you think, if it's the same person, it might be the same type of thinking. And we want actually, right, to have more minds looking at the code and more ideas. So let's see how it looks. Let's first of all see how it looks when we have good coverage. And here is work that we have done for Go token. We have here more than 22 rules, and we checked it against 30 mutations, all automatically generated, but we do also manual. And only 2 rules didn't catch any bugs. So those rules, I might go back and look at them again. And I might do a manual bug injection just to make sure they are not those limited scope. We know that there is a case that it's checking. We know that it passed Sanity. But still, we wanna do some kind of another validation. The other thing that I'm looking at those patches, mutations that we didn't catch. There might be here something very interesting that actually make me think of another property that I need to check. Okay, we might sometimes notice that it's not very interesting, or that it's not something very critical. Maybe we know that the code is okay and it's not worth the effort, but it is good to look. The other thing I'm looking at is I'm also asking myself, is the mutation caught? Are they caught by the rules I'm expecting? Let's take, for example, I'm just guessing here, this mutation, and I see that it was caught by a set of rules, and I might, looking at this code, I know my code, I might say, wait, I was expecting also this rule to catch this mutation. That is the way we are working, and we suggest to work with the Gambit. It's not only reaching here some nice numbers. It's very hard to reach the 100 coverage. The thing that is important here is to use this information to improve our rule. Okay. And if we look at Raft, we can actually see some interesting things that will highlight those things that we have discussed. So we run it only on a few, and as expected, most of them were not caught. Notice here, you remember we had this rule, check current index cannot be 0. So changing the stored index to 0 is indeed violated, and this is what we expect from this rule. But now we see how limited the scope is because there is another mutation that just changed it to 1. Okay, but this is not caught by this rule. So having it a fixed number, not 0, is okay for this set of properties, which doesn't make sense, right? It means that this rule has a very limited scope. Okay, any questions on mutations? Okay, great. So the last feature, and this is actually a feature that is in beta, this is what we call coverage information. And this is actually, we are using an underlying SMT solver. We are asking what part of the code was actually used in the proof. Okay, so let's take a look on this simple example. We have X defined as U into 56. We have it compute something, and then we just assert that it's greater or equal than 0. Okay, so we know, right, it can never be violated, giving it's defined as a uint. So what we expect to see that nothing in some complex code is actually used in verifying this property. Okay.
So maybe I just, maybe just to those of you who are not familiar with SMT, this is a technology, but if you are familiar with techniques like artificial intelligence, there are things like coin of influence. Essentially, what we are trying to understand, how are when the solver is telling you that something is right, the issues that how does the solver it, and how does the solver conclude that? When the idea is that the solver is trying to give you sort of the reason why things are correct, and if something is not used in the reasoning, it is fishy. That's the idea.
Yes, exactly. So here we can look at this on Raft. So we will improve this, but it does show some very interesting things. Let's just jump to that even burn. It's underscore burn. Okay. And we see that it is not covered. We do see that there are areas that are covered, and we can see due to what. So here, for example, this line is covered due to this check total. Okay, and so we know which rule covered it, and we know we can also see lines that are yellow, meaning that sometimes they are used, but sometimes they don't really matter. What else? Red are never used, so name is okay. We can also see the lines in the spec file. Sorry that I have to scroll a lot. Okay, where's the spec file? Okay, here again, we see that this require is not used for proving this assert. Okay. This is also nice. And now we can also see, after the additional rules, we can see if we, so this is on underscore burn. I did see that some lines are more covered now. Okay. So This is the idea. It can also help. It can also help understand where we need to focus on, which lines are definitely not covered, where you want to see more greens. And it basically helps. We can run it on a wool-to-wool basis, and it helps us see what exactly was used in proving this wool. Now, what happens is that there can be multiple proof that can be selected. So that is also something that can be confusing, but overall, it's another tool that we are working on, and we will keep on working on various techniques to help check the spec and make sure that you have good coverage. Yeah, so just to summarize, we are welcome everyone to use the Certora Prover, but we do encourage learn how to write specification. You can also reach out on the Discord with questions. We give support. We'll have more lectures on how to use correctly the prover and use all our tooling and more. And basically treat your spec like you treat your code. It has to be complete. It has to be tested. It has to be reviewed, and it's better even have it audited by someone, right? The equivalence to code code review. Okay. Any questions?
Maybe just follow on this, that besides Certora, there are other teams that you can check that are actually able to read. We have worked with other teams and that know how to read our rules. So even if you don't work with us and you work with other teams, and we usually, when we do auditing, I mentioned that we produce a formal verification report. But even if you are self-serve or free customer, you can approach other teams, that auditing firms that know how to read rules and to review the rules.